Alright guys, so in this video we're going to go over crossover design. So just a brief overview here, but some experiments have the potential to be affected by the time period between the treatments. So a good example of this is an experiment testing the effects of a drug where each subject is exposed to two different drugs, two different treatments, and the time period between the treatments could influence whether the first treatment affects the response of the second treatment. So just a brief illustration of this can be seen down here, where you would give your subjects the first treatment, then you allow some period of time to pass, and then record your observation. And then you allow a washout period, so another period of time to pass, which allows the carryover effects from the first treatment here to ideally be eliminated by the time that the second treatment is administered. So after that washout period, you administer your second treatment, and then again wait a period of time, record your observation, allow another washout period, administer your third treatment, so on and so forth. And so to design an experiment where time periods are a factor, we introduce the crossover design. So some key features of the crossover design can be seen here. But firstly, crossover designs must be balanced by ensuring that each treatment occurs at least one time in each time period. And crossover designs must also balance the carryover effects, where each treatment pair must occur an equal number of times throughout the experiment. So I'm just going to briefly illustrate that, but you can see that A, then B happens. So treatment A, then treatment B happens, treatment A, then C once, treatment A, then C twice, treatment C, then B once, treatment C, then B twice. And you can see that for every pairwise comparison that it occurs exactly twice. So that's what I mean by balanced for carryover effects. So every pairwise set of treatments occurs the same number of times throughout the experiment. And so to achieve that, crossover designs may use one or more Latin squares to balance the carryover effects, and it can be shown that experiments with an even number of treatments require only one Latin square, whereas experiments with an odd number of treatments, as is the case up here, they require two orthogonal Latin squares. All right, so we're just going to jump right into an example here, but our research institution is interested in studying the effect of three different drugs, A, B, and C, on cortisol levels. To investigate the effects, a researcher studies 6 mice labeled 1 through 6, where each mouse is exposed to each of 3 drugs in a randomly assigned order, allowing for these drugs to be exposed at 3 different time periods labeled 1 through 3. The experiment is performed using 2 rounds, where the first round is completed using the first 3 mice, and the second round is completed using the remaining 3 mice. So here's the design of the experiment. You have 3 drugs labeled A, B, and C, tested on each of the subjects, a population of 6 mice labeled 1 through 6, 3 time periods labeled 1 through 3, and 2 round effects labeled 1 and 2 that result from repeating the Latin square design. So what this looks like, but basic is you have a Latin square design. You construct a Latin square where the first 3 mice are each exposed to a different drug. Then you allow your time period to pass, record your observation, allow a washout period to pass, and then you administer your second set of drugs. And then again, wait a period of time, record your observation, and then administer the third set of drugs until your Latin square is completed. So this is repeated again until you have your two Latin squares, so 1 and 2, and then that's the data that you're going to analyze. So in order to analyze the data, we have to understand the model. Now the model is very similar to a replicated Latin square design, where we have YIJKL is the observation of the ith drug, jth mouse in the kth time period, and lth round on the amount of cortisol. Mu is the overall mean, tau I is the effect of the ith drug on the amount of cortisol, beta j nested in an L is the effect of the jth mouse in the lth round on the amount of cortisol, alpha k is the effect of the kth time period on the amount of cortisol, gamma L is the effect of the lth round on the amount of cortisol, and epsilon IJKL is a random error which follows a normal distribution with a mean of 0 and an unknown standard deviation of sigma. So also in this model, like many of the Latin square models, we also assume that the standard deviation sigma is the same across all treatments, all blocks, and all replicates. So methods, mice, time period, and rounds in this case. And then we're just going to show you how to analyze the data. So basically, to fit the statistical model to the data, you're going to put the data into your best friend Minitab. It's going to look very similar to a replicated Latin square design input. So you have a column for your round, a column for your mouse, a column for the time period, a column for the drug, and a column for your response, which is the amount of cortisol in this case. And then you're just going to go to stat, ANOVA, general in your model, fit general in your model. And then you're going to choose your responses and factors. So the response in this case is cortisol, and the factors are round, mice, period, and drugs. And one important thing that's not shown here, but the mouse or the mice are nested in the rounds. So you'd want to make sure that you go to nest and make sure that the mice are nested in the rounds. And then after you've got that all set up, you're going to hit go, and here's the output that you get from Minitab. So in this output, we can see that, let's see a couple key things here. So the round effect is insignificant. The mice nested in the round is insignificant, and the period is significant at a 10% significance level, or the time period is significant at a 10% significance level. So you can state these formally. I'm just going to do it for one of them. So since the p-value for the mouse and round blocking effects is larger than 0.05 at the 5% significance level, the sample data does not provide sufficient evidence to conclude that the blocking effects of the mice and round are statistically significant. And then you can go through and do a similar type of an analysis for the time period blocking effect. So then once you've established which blocking effects are significant, you can test whether the treatment effect is statistically significant. So in this case, we can see that it certainly is. It's approximately 0. So then we would just say, since the p-value for the drug is smaller than 0.05, at the 5% significance level, the sample data provides sufficient evidence to conclude that the treatment effect of the drug is statistically significant. So in other words, the mean amount of cortisol found is significantly different among the 3 drugs. So last but not least, we need to test the assumptions of the statistical model. So in this model, we assume that the random error follows a normal distribution with a mean of 0 and has an unknown standard deviation of sigma. And additionally, we also assumed that the standard deviation sigma is the same across all treatments, all blocks, and all replicates. So to test these assumptions, we use residuals. We've done this many times. It's the same type of analysis as for Latin square or replicated Latin square. So you're going to check the equal standard deviation assumption of the random error and the blocking effects and so on and so forth. So we perform Levene's test for equal variance to test whether standard deviations are statistically different. And what we find is that for all of the blocking effects and the treatment effect, they are all insignificant. So since none of the p-values are less than 0.05, at a 5% significance level, we do not have sufficient evidence to conclude that the equal variances assumption is not valid. Therefore, we do not reject the equal standard deviation assumption. So once that's been established, we move on to checking the normality assumption for the random error. So to do this, we use the residuals to make a histogram and normal probability plot. So since the normal probability plot, as we can see here, a histogram approximately follows the behavior of a normal distribution, we do not reject the assumption that the random error follows a normal distribution. Therefore, the conclusions drawn from the ANOVA test are valid. So that's basically it for the crossover design, guys. It's basically it's very similar to what we've seen before with Latin squares and replicated Latin squares. The key thing to remember about the crossover design is that time periods are involved, and that you should make sure that the design is balanced for carryover effects. But other than that, it's a very similar analysis to a Latin square or replicated Latin square. So you can work through this example here and compare your answers with what we've got using the data that we've provided, or you can try the problem at the end of these slides and see if you can work that out on your own. All right, guys, so that's it for the crossover design, and next we'll move on to the Graco Latin square design.